1. And pretty much what we're gonna discuss here is first basic laws of physics and assumptions. So we're pretty much gonna be talking about the fundamentals to understand the slap, and then the video of the object moving in constant velocity, and then the code initially before it being modified, and discussing what should be added to it to make it work to create the computational model. And then we're going to compare the observed values from the video to the code's computed values. And then we're going to be talking about what ifs and general conclusions. So, first of all, the formulas we're going to be using for this lab are Newton's second law and then change in position kinematic equation. As you see, this is F net is equal to the momentum divided by t, and then final position is equal to the initial position plus the average times delta t. This is pretty basic. And so I believe we need to be looking at this force body diagram to understand why F net should be equal to 0 in this case. And so these from each direction, the forces should be evened out. So this is the body, and for example, F floor, F earth, these two should be evened out to make sure the momentum stays equal, stays constant. And delta t cannot stay at 0, obviously, if the body is moving, because t would be a positive number in our case. And so for velocity to stay constant, forces from each side of an object should be evened out, so the momentum should be then 0 to maintain F net equal to 0, which would lead to our constant velocity. And this is further explained here. So we pretty much substitute with some basic formulas here. F net is equal to F net times delta t is equal to the change in momentum, and then F net times t is equal to pf minus pi, and then we pretty much derive this to make these substitutions to derive this conclusion that vf is equal to vi, because this is how we know we got constant velocity. And so this is pretty much the object moving in constant velocity. You can see here the graph displays constant velocity, and these ups and downs pretty much represent human error. Velocity is not exactly constant, like not perfectly, but it's relatively is. It looks like it, but obviously due to human error and the pushes and pulls, it cannot be exactly reached. But the computational model we'll be looking at will be able to do so. And so these are the observed values from the video. This is S, M, so seconds and distance. And this is the code we'll be looking at. So we pretty much got to modify this initial vector, the t time, and also make sure to use the accurate formula to compute the values of the constant velocity of the object under constant velocity. So t and the distance of the object at that particular time. And so these are the constants that we need for the code to work. So pretty much t is pretty easy to derive from the video, and it's pretty much how long the video is, 0.57. And then there is the average, which is pretty much distance divided by time. So we get 0.228. And yeah, pretty much substitute in this. You can see like up here the average, and then there's what the computational model does. Once you have these values, it shows you like constant velocity and then the computed values by the computer. So pretty much more accuracy than what my video did, because it's it consists of human errors. So these are the values, and then you can see that the orange line is pretty much perfect because it's computed, and then there's the blue dots, which is what my video has made. And what if x and y values are flipped? So pretty much this is a change of x values. It turns negative, and then when you change the y values, it also turns negative, but in a different way, as you see here. And what does this mean? And what if we assume that net force is equal to zero, and can we determine the number of pushes and pulls of an object? Well, I believe we can, because they're pretty much an infinite number of pushes and pulls of an object, because there's always gravitational force of different objects being exerted to not to the rest of the objects. So there's pretty much an infinite amount of objects exerting